All right, let's wrap up this chapter. We're going to talk a little bit about MO theory again, and I know this is not everyone's favorite subject. We're going to breeze through it a little bit, but there are some really important aspects of these cycloadditions that we need to discuss. Looking at the Diels-Alder reaction again, right, with the butadiene and ethylene. So this would be a very, very simple diene and dienophile reaction. The diene has 4 p orbitals, and those 4 p orbitals, when they come together, make 4 molecular orbitals, right? And so these are what we talked about, psi 1, 2, 3, 4. We see the HOMO and the LUMO, right? With our 4 electrons, we want to fill the lowest 2 psis there, the lowest 2 molecular orbitals. And so the HOMO, the highest occupied molecular orbital there, is psi 2. The LUMO, the lowest unoccupied molecular orbital, is psi 3 of 1,3-butadiene. Now for the dienophile, we're just going to say ethylene, or that's the common name for ethene, just a plain old carbon-carbon double bond, has 2 p orbitals, and so there's 2 molecular orbitals. It has its own HOMO and its own LUMO. Right? And so we have to really understand for the Diels-Alder that the HOMO of one must interact with the LUMO of the other. And that's truly what is actually happening. When we do an organic chemistry reaction, molecular orbital theory has been developed to help us understand that when one set of electrons goes to react, and we do the curved arrows, right? Let's just draw them real quick. When we do the curved arrows to say, you go dump in here, right? Or you go dump in here, whichever one we're dealing with, it's really understanding that the electrons are trying to destabilize the bonding orbitals. And how we destabilize the bonding orbitals is by literally dumping them into anti-bonding orbitals. And so with the electron withdrawing group, the dienophile's LUMO will accept electrons from the diene's HOMO. All right, so the diene is usually more electron rich, and so it is looked at as the nucleophile to start off this idea. And so we literally see the diene HOMO electrons popping in electrons to the electrophile ethene's LUMO, okay? Now it's this interaction, the HOMO and the LUMO, that we want to see occur, okay? So we're going to take these orbitals and we're going to draw them on butadiene. I'll shade these, like blue is shaded and red will be unshaded, right? And we're going to take these two, right? And we're going to try to see how can they interact, right, in such a way that would be helpful. Look at these better drawings, more beautiful, right? So the phases of the reacting MOs must be symmetrical, right? So if there is a conservation of orbital symmetry, then the symmetry is allowed, the reaction is allowed, okay? So looking at the HOMO of butadiene and the LUMO of ethylene, we see that the blue matches with the blue and the red matches with the red, and that's what we want to see. And the carbons are changing their hybridization from sp2 to sp3, all right? So this is symmetry allowed when we took the HOMO of one and the LUMO of the other. I would always tell you which HOMO and which LUMO to use. You just might need to be able to line them up and say, is symmetry allowing? And we'll have a lot more practice in class. Similar to the Diels-Alder, the 4+2 cycloaddition, the reaction below here with a 2+2 cycloaddition is very, very similar, okay? So boop, boop, right? What we've added was these 2 new sigma bonds of cyclobutane. Now the reacting MOs, the HOMO and the LUMO, can be analyzed just as the same before, okay? So we took the HOMO of one ethylene and the LUMO of the other, and we said, will symmetry allow this? Well, look at the top of one and the bottom of the other. Do they match up? Is there a way to match them up? Looking at this here, I don't see it. It doesn't work. One matches up, but then the other one doesn't, right? They're not the same as they were before. So because the phases don't line up, symmetry is forbidden here with the straight up reaction, all right? 2 + 2 cycloadditions are only possible when light is used. Remember, light was able to excite an electron from the ground state to the excited state. Now we have a new HOMO, right? And so technically, if we have a new HOMO from the excited state, look at that, symmetry is now allowed because they match up. They're the same damn thing. So light can be used in certain reactions to allow for symmetry. All right, so we're going to talk about that a little bit more in class when symmetry is allowed. And we're going to see, can light be used to excite an electron to create a new HOMO, a new excited state HOMO that then would allow symmetry, all right, if symmetry is not allowed in the ground state. For Diels-Alder, the 4 + 2 cycloadditions are allowed, symmetry allowed in the ground state. For 2 + 2 cycloadditions, light is necessary to excite the electron. All right, electrocyclic reactions. This pericyclic process occurs when conjugated polyenes undergo cyclization. So again, we could have 1, 2, 3, 4, 5, 6 compounds and make a cyclic structure with 6 carbons. We can also do it with 4. So we can have a triene, 3 pi bonds, 6 atoms, or a diene, 4 atoms, 2 pi bonds. All right, overall, a pi bond is converted to a sigma bond. Now, when substituents are present and on these terminal carbons, stereoisomers are possible, okay? So let's look here in this middle section. I want to look at this setup right here where we have the 6-membered ring that could possibly form, right? And I'm going to do the curved arrows, okay? Curved arrows, again, can be clockwise or counterclockwise. 1, 2, 3, 4, 5, 6. All right, let's just draw those again. Clear some stuff up. Pi bond between 1 and 2 can go to make the new sigma bond between 1 and 6. I'm just going to highlight it there. That would cause the pi bond between 5 and 6 to move over, between 4 and 5, and the pi bond between 3 and 4 to move up to 2 and 3. Awesome, right? Now, notice these methyl groups are opposite of each other. When heat is used, those methyls become on the same side. When light is used and we excite the electron in one of the HOMO to the LUMO, right, and create a new excited state HOMO, the methyls become opposite of each other. Okay, we'll talk about why this occurs in just a little bit, but it has to do with symmetry. All right, let's look at the bottom one. Methyls are different, right? Methyls swapped places. One of them did. Again, same curved arrows. Pop it over, pop it up. 3 arrows there for those 3 pi bonds reacting. If we used heat, those methyls that are both pointing up would be 1 wedged, 1 dashed, right? If we used light and excited the HOMO, then we get opposites, okay? Same thing or same style occurs for our 4-electron system, right? conservation of orbital symmetry is the only way to explain this observation, okay? So when we're looking at orbital symmetry, we're going to be looking at the ground state, heat, ground state HOMO, to understand what happens to those substituents. When we use light, we are going to look at the excited state HOMO, the previous LUMO, all right? So considering the first stereochemical outcome of the thermal cyclization, right, heat with the 3 conjugated pi bonds, okay? When we're looking at this first setup, we have 3 pi bonds, right? And we have heat, so ground state, HOMO. What happens when the methyl groups are on opposite sides? They become cis. And when the methyl groups are on the same side, they become trans. Let's look at the MOs to understand why, okay? This is the HOMO that we had already discussed before. This is the HOMO of 1,3-butadiene, all right? So looking at the methyls here, these are the methyls that are opposites. We want to look and be able to actually overlap the phases, okay? And so what is going to happen to those methyls when we try to overlap the phases, whether those are the 2 blues or the 2 reds? It doesn't matter which one we start to think about. What happens? This is what we call disrotatory. One moves counterclockwise, the other moves clockwise. We're trying to bring those 2 bottom lobes of red together to make a bonding orbital, okay? We have to bring them in phases. So it's either bringing the 2 blues or the 2 reds. Sorry, I chose the 2 reds. Disrotatory, one rotates clockwise, one rotates counterclockwise, is what is happening to give the cis product, okay? Notice how this group and this group are both rotating downward. Disrotatory. That's how they become cis, okay? For the 4 pi electron system, okay? This is the HOMO for ethene. So again, looking at where those groups are, now we're looking at a different HOMO and we're trying to understand what's gonna happen to the methyls, what's gonna happen to the substituents. Notice in this structure, I really like these images in the textbook because it ignores the inner p orbitals. Those don't matter. We're only looking at the formation of the sigma bond in these electrocyclic reactions. This is conrotatory. They're both moving the same way, right? Because we're trying to get this red lobe to match up with that red lobe. So one has to rotate up and the other one also has to rotate up. So the 2 red lobes come together. Now, what does that mean for the methyl groups? This one's going down, this one's going up. They're opposites, they're trans. Okay, so really what's important to understand is this overall. Under thermal conditions, a 6 pi electron system would be disrotatory. A 4 pi electron system is conrotatory. All right, I like to, when we get together, we'll use a lot of our hands to be able to understand some kinesthetic learning with this. I know it's rather difficult, but what's really important is to have your diagrams with you when you practice so that you can see the disrotatory and the conrotatory. Under photochemical conditions, using light, getting the excited state, the energy excites an electron from the HOMO to the LUMO. So what was the LUMO becomes the new excited state HOMO, right? So this was the HOMO we were just dealing with the 6 pi electron system. This is now the new HOMO. It's the next one over, right? It's the psi 4. Again, what happened? Ooh, we now become conrotatory. Interesting. Disrotatory for heat, conrotatory for light. So disrotatory for heat, conrotatory for light. Same switching of stereochemistry is also observed with the 4-pi electron system, conrotatory for heat, disrotatory for light. Remember, conrotatory is when they move the same. Disrotatory is when they move opposite in terms of which way are you rotating. All right, so here are the Woodward-Hoffman rules to summarize that trend for electrocyclic reactions. You can, of course, use this, and we'll talk more in depth about them in class. Sigmatropic rearrangements are where we have a net overall no sigma bond added or broken, or one is broken, one is added. Same with the pi's. 2 pi's are broken, but 2 pi's are added. Okay, so overall no net change. Just the location of these bonds are going to change. And again, same curved arrows. The notation for sigmatropic rearrangements is what we really just want to talk about. There's not too much going on with this in terms of allowed or not allowed. But counting the atoms is important. We count from where the sigma bond broke and to where the sigma bond is formed. All right, so we're seeing this type of a rearrangement where we have 1, 2, 3 atoms on the top, and they're being connected to 1, 2, 3 atoms on the bottom. So this is called a 3-3 sigmatropic rearrangement. Again, start counting where a sigma bond broke and then end where the new sigma bond started. There we go. We can have a 1-5 sigmatropic rearrangement. 1-5, again, where did the sigma bond start? And then where is the sigma bond going? There's your 1 and your 1, 2, 3, 4, 5. Okay, or you could count it the other way in red. The Cope rearrangement is specifically a 3-3 sigmatropic reaction where all 6 atoms in the cyclic transition state are carbons. Equilibrium favors the side with more substituted alkenes. That's all we need to know about that one. A Claisen rearrangement is also a 3-3 sigmatropic reaction, and it's involving an oxygen analog. So it's the same thing as the Cope arrangement, it just includes an oxygen. And so equilibrium will favor the formation of the carbon-oxygen double bond simply because it's more stable than the carbon-carbon double bond. Claisen rearrangements are often observed with aryl allylic ethers as well, meaning that you could technically see a rearrangement occur if you have a allylic position outside of a 6-membered ring. We will practice viewing these a lot in class, but again, this rotation must occur so we get the cyclic structure here. 1, 2, 3, 1, 2, 3. And so we get the rearrangement, right? This does break aromaticity, but then a tautomerization happens to go from the keto to the enol form. The only reason why the enol is more stable here is because it's aromatic, which we will talk about in the next chapter. All right, just to wrap up our discussion of sigmatropic rearrangements, 2 pericyclic reactions actually occur in the biosynthesis of vitamin D. You've always heard, or hopefully you've heard of vitamin D as being the sunlight vitamin, the one that you have to go outside to get. It's not because the sunlight has vitamin D in it, it's because vitamin D is synthesized by our bodies in the top dermal layer of our skin, right? So how they are reacted is with light, and the best light to do that is with sunlight because it's free. So heat is not important, right? We can't do heat for this. You can't just sit in your nice warm house. You got to go out and get that sunlight. You got to get those UV rays, right? So light is needed for the reverse of an electrocyclic reaction, where we open up that 6-membered ring. This sigma bond breaks. Awesome. And we make our 3 pi electron system. And then we do actually a 1,7 sigmatropic. Here's your 1 and 1, 2, 3, 4, 5, 6, 7. You don't need to know this reaction. It's just really cool to know how vitamin D is actually formed in our bodies. And how is it formed? An electrocyclic reaction followed by a 1,7 sigmatropic rearrangement. Soup's cool.